Picture this. It's March 1943, and Lieutenant James Howard is staring out of his B-17 bomber at 23,000 feet over occupied France. His crew has just spent 8 brutal hours flying through freezing temperatures and dodging German fighters to reach a critical ball-bearing factory near Paris. The bombardier calls out confidently, "Bombs away!" 30 seconds later, Howard watches through binoculars as their entire payload, 12,500-pound bombs, explodes harmlessly in a wheat field half a mile from the target. Complete miss. They're not alone in this failure. Of the 228 bombers in his formation that day, only 19 actually hit anything remotely close to their intended target. That's an 8% success rate, and honestly that was considered a pretty good day by 1943 standards. The reality of American strategic bombing in early World War II was absolutely brutal, and nobody in command wanted to talk about it. Back in Washington, generals were confidently telling Congress that precision daylight bombing would win the war decisively. They had impressive charts. They had detailed scale models. They had unwavering confidence. But over Europe, exhausted crews were learning a harsh, undeniable truth. Dropping bombs from 4 miles up while traveling at 180 miles per hour with German fighters attacking you and flak exploding around your aircraft made accuracy basically impossible. The Army Air Forces had carefully calculated they needed a circular error probable of about 1,000 feet to effectively destroy industrial targets. In plain English, that meant half your bombs needed to land within 1,000 feet of the aiming point. Sounds reasonable on paper, right? Completely wrong. By summer 1943, the actual CEP for 8th Air Force missions was hovering around 3,200 feet, more than triple the requirement. Some missions were worse, much worse. During the first Schweinfurt raid in August 1943, bombers dropped 724 tons of high explosives on ball-bearing factories that supplied 40% of Germany's war production. Post-mission reconnaissance photography showed that less than 200 tons actually hit inside the factory complex. The rest cratered residential neighborhoods, empty fields, and destroyed a medieval church 3 miles away. 60 bombers were shot down that day, 600 men killed or captured for years in POW camps, and the factories were back to full production within 6 weeks. Crews started calling it the aluminum cloud approach because that's essentially what it was. You flew in tight formation, hoped desperately the lead bombardier knew what he was doing, and when he dropped his bombs, everyone else toggled theirs immediately afterward. The theory said that even if individual bombs scattered wildly, sheer volume would statistically overwhelm the target. But German factories weren't enormous targets sitting in open fields. A typical synthetic oil plant might cover 40 acres. Sounds big until you realize that at 3,000-foot accuracy, your bomb pattern was spreading across 300 acres. You were essentially carpet bombing and praying something important got hit. The human cost made it even worse. Every single mission meant 10-man crews flying through walls of flak, those black puffs of 88mm shells that could shred a bomber's aluminum skin like tissue paper. Crew survival rates in 1943 were absolutely terrifying. Statistically, a bomber crew had only a 1 in 4 chance of surviving their required 25 missions. And for what? To watch your bombs disappear into clouds, or worse, to see them hit and know with certainty you'd just obliterated a residential block while the factory next door kept running at full capacity. The morale was collapsing faster than the bombing campaign itself. The Norden bombsight was supposed to change everything about strategic bombing. If you've ever wondered why American bombers kept flying suicidal daylight missions while the British wisely switched to night bombing, the Norden is your answer. This device, officially designated the Mark 15 Norden bombsight, was essentially a mechanical analog computer that weighed 50 pounds and cost $8,000 per unit in 1943 dollars. That's more than most American houses cost at the time. The Army Air Forces were so completely obsessed with this technological marvel, they spent $1.5 billion developing and producing it, making it one of America's most expensive weapons programs. For context, the entire Manhattan Project cost $2 billion. Carl Norden, a Swiss engineer working in New York, had designed this optical computing marvel in the 1920s with a genuinely brilliant concept. The bombardier would lie prone in the nose of the aircraft, peer through the sight's eyepiece, and manually track the target while a bombsight automatically calculated drift, altitude, airspeed, and trajectory in real time. Here's where it got genuinely fancy. The sight was actually hardwired into the aircraft's autopilot system. During the critical bombing run, the bombardier could make tiny corrections using a control panel, and the bombsight would physically fly the aeroplane to compensate for wind drift. In theory, this gave you perfect pickle barrel accuracy. Army demonstrations showed skilled bombardiers dropping practice bombs into 100-foot circles from 20,000 feet. Promotional materials distributed to Congress literally claimed you could drop a bomb into a pickle barrel from 4 miles up. The security around Norden sites was absolutely paranoid, bordering on obsessive. Bombardiers took a formal oath, separate from their standard military oath, never to reveal anything about the device to anyone. Before every mission, an armed guard would bring the bombsight to the aircraft in a locked metal case. If the bomber was going down, the bombardier's explicit orders were to destroy the site with a thermite grenade before bailing out. Several bombardiers actually died trying to follow those orders, staying with burning aircraft too long while attempting to melt their Norden sites. The military genuinely believed that if the Germans captured one intact, they'd copy it, and America's strategic bombing advantage would evaporate overnight. Here's the crushing irony. The Germans already had the Norden secrets and didn't care. A German spy named Hermann Lang had stolen the complete blueprints in 1938, and German engineers looked at them, shrugged, and went back to their own Notfernrohr 7 bombsight design. Why? Because they'd already figured out what American crews were about to learn the hard way. The Norden's precision was completely theoretical. It assumed you'd have unlimited time over the target, absolutely no defensive fire, perfect visibility, and perfectly stable air. Combat over Europe offered exactly none of those conditions. The first reality check came from the targets themselves. German factory complexes weren't sitting ducks in open fields. They had industrial smoke generators that could blanket entire industrial zones within 5 minutes of raid alarm. By late 1943, German defensive doctrine required every major target to have enough smoke capacity to obscure visibility for 30 minutes minimum. Bombardiers would spend the entire approach watching their target crystal clearly. Then, at the critical moment, poof, it vanished under artificial fog. Now you're guessing, and the Norden bombsight can't compute best guess. Then there was combat itself. The Norden needed a straight, level bombing run of at least 3 full minutes to calculate properly. 3 minutes of flying straight and level over Germany meant 3 minutes of being a perfectly predictable target for every flak gun below. Pilots quickly learned that evasive action kept you alive but made the Norden completely useless. The device couldn't compensate for sudden altitude changes or sharp turns. So crews faced an impossible choice: fly steady and die, or maneuver and miss. German flak gunners weren't just shooting at American bombers, they were conducting an industrial-scale execution. By 1943, Germany had constructed the most sophisticated anti-aircraft defense network in human history, and it was absolutely shredding the 8th Air Force at an alarming rate. The backbone of this system was the 88mm flak gun, properly called the Flak 18, 36 or 37 depending on the variant. You've probably heard of the 88 as a tank killer, and it was devastatingly effective in that role, but its primary job was murdering bombers at altitude. Germany produced roughly 21,000 of these guns during the war, and about 10,000 were strategically ringing critical targets across occupied Europe. Here's what made the 88 so absolutely terrifying. It could fire a 20-pound high-explosive shell up to 32,000 feet at a sustained rate of 15 to 20 rounds per minute. Each shell was fitted with a precision time delay fuse that German crews would manually set based on the bomber's altitude. The shell would climb, reach the predetermined height, and detonate into thousands of razor-sharp fragments traveling at supersonic speeds. A single fragment the size of your thumb could punch through aluminum skin, sever control cables, rupture fuel tanks, or kill a crew member instantly. And German gunners weren't firing one at a time, they were firing in coordinated batteries. A typical German industrial target like the Ruhr Valley would have 40 to 60 heavy flak guns positioned in overlapping fields of fire. Fire control radar, the Würzburg system, could track bomber formations from 40 miles out and feed continuous data to gun calculators. The Germans literally had mechanical computers at each battery that would crunch altitude, speed, and heading data, then spit out firing solutions. Crews could set their fuses and start firing before American bombers even saw the target. On a major raid, you'd have hundreds of guns throwing up thousands of shells, creating what bomber crews called flak fields, entire chunks of sky that turned black with explosions. The math was simple and brutal. If you flew through heavy flak at 18,000 feet, you were in the optimal kill zone where German guns were most accurate. At that altitude, crews reported seeing flak bursts so thick you couldn't see through them. The sound was like being inside a metal drum while someone beat it with sledgehammers. Survivors described it as continuous thunder mixed with the metallic ping of shrapnel hitting the aircraft. Navigator John Morris from the 301st Bomb Group wrote in his diary after a mission to Bremen counted 127 holes in our ship. Don't know how we made it. Jenkins bled out in the waist before we crossed the channel. He was 19 years old. So American planners made what seemed like a logical decision: climb higher. By mid-1943, bomber formations were routinely operating at 25,000 to 27,000 feet, occasionally pushing to 30,000. Up there, you were above most of the flak's effective range, and German fighters had serious trouble with performance at extreme altitude. The catch? At 25,000 feet, the air temperature is minus 40 degrees Fahrenheit, and the air is so thin that even with supercharged engines, aircraft performance suffers dramatically. Crews needed heated flight suits and oxygen masks for survival. But the real killer was what altitude did to bombing accuracy. Remember that Norden bombsight promising pickle barrel precision. At 25,000 feet, every variable that made bombing difficult at 18,000 feet got exponentially worse. Wind speeds at high altitude weren't the 20 or 30 miles per hour you'd experience at lower levels. They were 80, 100, sometimes 120 miles per hour. Jet streams weren't even understood yet. Crews just knew that sometimes they'd drop bombs and watch them drift sideways for miles. Visibility turned unreliable. Clouds that looked thin from above would completely obscure targets. Temperature inversions created atmospheric layers that bent light, making accurate sighting nearly impossible. Nobody planned the offset bombing technique. It was born from desperation, confusion, and one navigator's mistake over Schweinfurt in October 1943. The second raid on Schweinfurt's ball-bearing plants was already a complete disaster. 291 bombers launched, 60 were shot down, and 17 more were so damaged they never flew again. That's a 26% loss rate in a single mission. But buried in the post-mission reports was something strange. One bomb group, the 305th, had accidentally approached their initial point, the spot where you start your final bombing run, from the wrong direction. Instead of the planned north-to-south attack, they came in from the northeast at roughly a 40-degree angle to the target. Their navigator, Captain Robert Williams, had miscalculated a wind correction during the approach. By the time the lead pilot realized they were off course, they were already committed. You don't turn a formation of 18 heavy bombers on a dime, especially with German fighters swarming. So Williams made a field decision. He told his bombardier, Lieutenant Charles Murphy, to aim using the crosswind correction knobs on the Norden site, but to deliberately offset the aiming point to the right of the factory complex. Basically, instead of aiming straight at the target and letting the bomb sight calculate drift, Murphy aimed at empty space beside the target and let the bombs drift back into it. The results were photographed by the strike cameras every bomber carried. While most groups that day achieved their typical 8 to 12% hit rate, The 305th bombs walked directly through the center of the factory complex. 42% of their ordnance struck within the target area. At first, analysts assumed it was luck, random chance, but Williams insisted it wasn't random at all, and he had the mathematics to prove it. See, the Norden bombsight had a fundamental design assumption that was killing accuracy at high altitude. It assumed you'd be flying directly at your target, with wind either pushing you along or slowing you down. Headwind or tailwind. The sight's drift correction calculated for that. But at 25,000 feet over Germany, winds were almost never perfectly aligned with your bombing run. They were coming from the side, pushing the entire aircraft sideways through the air. This created what's called crab angle. The aircraft's nose would point slightly into the wind to maintain a straight ground track, kind of like walking forward while leaning into a strong side wind. The problem was that when you released bombs from an aircraft in a crab angle, they inherited both the forward velocity and the sideways drift. The Norden could calculate the forward trajectory beautifully, but its side drift compensation assumed you were maintaining a heading directly at the target. When you were crabbing into a crosswind, the sight's calculations were off by hundreds of feet. The stronger the crosswind, the worse the error. And at 25,000 feet, crosswinds were always strong. Williams' accidental discovery was simple but revolutionary. If you deliberately approach the target at an angle to the expected wind direction, and you offset your aim point perpendicular to your flight path, you could use the crosswind to walk your bombs onto the target. Instead of fighting the wind drift, you weaponized it. The bombardier would identify a reference point, a road intersection, a river bend, a distinctive building, that was directly crosswind from the actual target. He'd aim at that reference point, and as the bombs fell through 4 miles of air, the wind would push them sideways onto the real target. The genius was in the geometry. At a 40 to 50 degree offset angle, the wind did most of the work. The bombs would drift predictably, and because you were accounting for that drift from the beginning, your dispersion pattern tightened dramatically. Instead of bombs scattering in an elongated oval along your flight path, they'd track sideways in a concentrated line. It was counterintuitive. You were deliberately aiming away from what you wanted to hit. But the physics were undeniable. The mathematics behind offset bombing weren't complicated, but they required bombardiers to completely rewire how they thought about the problem. Traditional bombing doctrine said, aim at the target and let the Norden calculate everything else. Offset bombing said, forget the target exists for a moment, focus on the wind triangle. Every bombardier had learned wind triangles in navigation school, but most treated them as theoretical exercises. Now those triangles were the difference between hitting a factory and obliterating a hospital 3 blocks away. Here's how the math actually worked. Imagine you're flying at 25,000 feet with a ground speed of 180 miles per hour, and there's a 90 mile per hour crosswind blowing from west to east. Your bombs take roughly 60 seconds to fall from release to impact. That's a full minute of drift time. In that minute, your forward momentum carries the bombs about 3 miles along your flight path. But that crosswind is also pushing them sideways at 90 miles per hour, which means 1.5 miles of lateral drift. Without offset correction, you'd aim at the factory, and your bombs would land 1.5 miles to the east in whatever happened to be there. The offset solution flipped the equation. Instead of flying directly at the factory, you'd approach at a 40 to 50 degree angle from the west, with the wind on your left side pushing you toward the target. Your bombardier would identify an offset aiming point, let's say a railroad yard that sat exactly where the wind would carry your bombs from. He'd track that railroad yard through the Norden sight, set the crosswind drift angle into the computer, and release. The bombs would leave the aircraft, start falling, and the crosswind would push them from the railroad yard toward the factory. If your calculations were right, they'd arrive at the factory exactly as they hit the ground. Wind speed measurement became absolutely critical, and that's where things got interesting. Navigators started using a technique called the double drift method during the bomb run approach. They'd take 2 drift readings at different points on the way to the target, basically measuring how much the wind was pushing the aircraft off course. By comparing those readings, they could calculate the wind speed and direction with surprising accuracy. Good navigators could get wind data within 5 miles per hour of actual conditions, and that precision was enough to make offset bombing work. The improvement in accuracy was staggering. 8th Air Force testing in late 1943 showed that offset approaches at 45-degree angles reduced CEP from 3,200 feet down to roughly 1,000 foot, almost exactly the 1,000-foot threshold that planners had originally demanded. Some particularly skilled bombardier navigator teams were achieving 800-foot accuracy on clear days. That might not sound impressive compared to modern GPS-guided weapons that land within 15 feet, but in 1943 it was revolutionary. It meant your bombs were actually hitting inside the factory complex instead of decorating the surrounding countryside. The technique required intense coordination between 3 crew members: the navigator, the bombardier, and the pilot. The navigator had to nail the wind calculations and identify the correct offset point. The bombardier had to trust those calculations completely and track a reference point that his instincts were screaming wasn't the target. And the pilot had to maintain an exact heading and altitude while flak was exploding around him, and every fiber of his being wanted to take evasive action. Training became the bottleneck. Bombardiers who'd spent months learning to aim directly at targets now had to unlearn that instinct. It was like teaching a basketball player to look at the backboard instead of the hoop. Your brain fights you every step. The Army Air Forces set up specialized schools in Florida and Arizona where crews practiced offset runs over mock German factories. They'd fly the patterns dozens of times until the geometry became intuitive. Veteran crews who'd already flown combat missions were pulled back to England for intensive retraining, which tells you how seriously the brass took this discovery. By January 1944, the 8th Air Force faced a problem that most organizations would kill to have. They'd discovered something that actually worked, and now they had to implement it across 12,000 men scattered across 40 airfields in England while simultaneously fighting a war. General James Doolittle, who'd taken command of the 8th in January, looked at the offset bombing data and made it his top training priority. He gave his operations officer, Brigadier General Fred Anderson, 6 weeks to retrain every bombardier and navigator in the theatre. Anderson's response was reportedly unprintable, but he got it done. The retraining program started with the lead crews, the most experienced bombardiers and navigators, who flew in the front aircraft of each formation. These were the men everyone else followed, so they had to master offset techniques first. Schools were established at each bomber base using a combination of classroom instruction and practical flights over English coastal ranges. The theory sessions covered wind triangles, drift calculations, and offset geometry until crews could work the math in their sleep. Then came the flying. The challenge was that England in winter offered terrible practice conditions. Cloud cover was constant, winds were unpredictable, and daylight was limited. But that actually helped in a perverse way. If you could hit targets through English weather, German weather would be manageable. Crews would take off at dawn, fly to bombing ranges off the coast, and make offset practice runs on floating targets or decommissioned old ships. Each crew flew minimum 3 practice missions before being certified for combat offset bombing. Some needed 10 before they got the feel for it. What made the retraining work was that combat veterans were teaching combat veterans. This wasn't some academy instructor with a pointer explaining theory. It was Lieutenant Murphy from the 305th Bomb Group, the guy who'd accidentally discovered offset at Schweinfurt, standing in a freezing concert hut showing other bombardiers exactly what he did. Captain Williams taught the navigator portions, walking men through his wind calculation methods using actual mission data. When students struggled with the counterintuitive nature of aiming away from targets, instructors would show strike camera footage from recent missions. Here's traditional bombing achieving 9% accuracy. Here's offset achieving 38%. The evidence was impossible to argue with. Doctrine changes happen similarly with training. The 8th Air Force rewrote their tactical bombing manuals in February 1944. Field Order 259, issued on February 20th, officially authorized offset bombing approaches for all missions where crosswind conditions exceeded 40 miles per hour. Group commanders received detailed briefing packages that included optimal approach angles for every major target in Germany. Schweinfurt had recommended approaches from the northeast at 45 degrees. The Ruhr Valley complexes worked best with 50-degree offsets from the west. Someone had done the homework. The implementation wasn't smooth. Older pilots, especially those who'd survived 1943, resisted changing tactics that they'd literally bled to learn. There's a famous incident from March 1944 where a 91st Bomb Group pilot refused to fly an offset approach to Brunswick, insisting on the traditional straight-in attack, because that's how we've always done it. His bombs missed the target by half a mile, and that pilot was quietly reassigned to non-combat duties. Doolittle was serious about this. Adapt or get out of the way. By April 1944, offset bombing had become standard operating procedure. Mission briefings now included dedicated wind analysis sections, where meteorologists would provide expected wind speeds and directions at bombing altitude. Navigators received pre-calculated offset approach headings based on forecast winds. If conditions changed en route, navigators had lookup tables to recalculate on the fly. The system was becoming systematized, which meant even average crews could achieve results that previously required exceptional skill. The results showed up in the data immediately. March 1944 bombing accuracy jumped to an average CEP of 1,250 feet across all 8th Air Force missions. A 60% improvement over December 1943. More importantly, the percentage of bombs hitting within target areas climbed from 11% to 27%. That still meant 3/4 of bombs were missing, but it represented a genuine revolution in capability. Factories that previously required 4 or 5 raids to seriously damage could now be crippled in 2. D-Day gave offset bombing its ultimate test, and the stakes couldn't have been higher. On June 6, 1944, the success of the entire Normandy invasion depended on whether Allied bombers could destroy German coastal fortifications before troops hit the beaches. These weren't just gun positions. They were reinforced concrete bunkers with walls 8 feet thick housing artillery pieces that could shred landing craft from 3 miles offshore. Intelligence had identified 49 major battery positions along a 50-mile stretch of coastline. Every one of them had to be neutralized or thousands of soldiers would die in the surf. The 8th Air Force drew the mission for Utah and Omaha beaches. They had a window from 5:50 a.m. to 6:30 a.m., 40 minutes to drop over 2,900 tons of bombs on fortifications that covered less than 2 square miles total. The timing was brutal because they'd be bombing in twilight with cloud cover forecast at 3,000 to 6,000 feet. Normal doctrine said you couldn't accurately bomb through clouds, but normal doctrine was about to get rewritten again. Offset bombing techniques combined with radar navigation aids made it theoretically possible to hit targets you couldn't even see. Here's how they planned it. Pathfinder aircraft equipped with H-2X radar would lead each formation. This radar could paint a rough picture of the coastline through clouds by detecting the boundary between land and water. Navigators would identify distinctive coastal features, river mouths, peninsulas, shoreline curves, and use those as offset reference points. The math was the same as visual offset bombing, except now you were doing it with radar returns instead of actual observation. Bombardiers would track the radar reference point, calculate the wind drift that would carry bombs from that point to the fortifications and release. The execution on D-Day morning was chaotic. Cloud cover was worse than forecast, solid overcast from 2,000 feet up to 10,000 feet in many sectors. Bomber formations had to descend to 12,000 feet to get below the worst of the weather, putting them in range of any German flak guns that survived the naval bombardment. Wind conditions were difficult. 25 to 40 mile-per-hour crosswinds from the northwest, pushing aircraft toward the beaches. That wind became the weapon. At Omaha Beach, the bombing results were initially reported as disastrous. Most bombs landed inland, cratering fields and roads behind the German positions. Post-invasion analysis suggested only 31% of fortifications at Omaha took direct hits during the air attack. But here's what the initial reports missed. The offset approaches from Utah Beach were devastating. At Utah, bombardiers used a 45-degree offset angle approaching from the northeast with crosswinds pushing them toward the beach. The bombs walked through the battery positions in neat lines, collapsing bunkers and destroying gun positions with 89% effectiveness. Of the 28 major fortifications at Utah Beach, 25 were knocked out before troops landed. The difference between Omaha and Utah came down to execution. At Omaha, bombardiers added a deliberate delay to their release points. They were terrified of hitting their own landing craft, so they held bombs an extra few seconds. That put the impact points 200 to 300 yards inland. Noble intention, catastrophic result. At Utah, bombardiers stuck to their calculated release points with no safety delays, trusting the math to keep bombs off the beaches. Their trust was rewarded. When the 4th Infantry Division hit Utah Beach at 6:30 a.m., they found German positions already destroyed. Resistance was light, casualties were minimal. The lesson was documented in a classified analysis completed in July 1944. Traditional straight-in bombing approaches at Omaha, even modified for safety concerns, achieved 31% effectiveness. Offset approaches at Utah, executed as trained, achieved 89% effectiveness. That's not a marginal improvement. That's the difference between a technique that barely works and one that decisively wins battles. The report concluded that offset bombing had reduced the number of raids required to neutralize fortified positions by a factor of 3. By summer 1944, every major Allied bombing operation incorporated offset techniques as primary doctrine. The raids on French rail yards before the invasion, the attacks on V-1 launch sites, the systematic destruction of German oil production, all used offset approaches as standard procedure. The technique even crossed service boundaries. 9th Air Force medium bombers adopted it for tactical strikes. RAF Bomber Command, which had dismissed American precision bombing as fantasy, started experimenting with offset methods for their own daylight operations. The desperate innovation born over Schweinfurt in 1943 didn't end with World War II. It fundamentally changed how humans think about dropping things from aircraft. When the war ended and analysts sat down to write the United States Strategic Bombing Survey, they found something remarkable in the data. Between January and December 1944, as offset bombing became universal across the 8th Air Force, the total tonnage dropped on Germany increased by 340%, while accuracy improved by 190%. You were dropping more bombs and hitting more targets. That combination broke German industrial production in ways that the early war's random bombing never could. The Cold War turned offset techniques from tactical necessity into strategic science. When the Air Force started planning nuclear strikes in the 1950s, accuracy became existential. A conventional bomb that misses by a mile just wastes resources. A nuclear weapon that misses by a mile might hit the wrong city. So Air Force bombing schools began teaching offset geometry as fundamental doctrine, on par with learning how to take off and land. Every bomber pilot in Strategic Air Command could calculate offset angles in his sleep because his training assumed he'd be delivering atomic weapons through Soviet air defenses where straight-in approaches meant death. The mathematics evolved with technology. When the B-52 Stratofortress entered service in 1955, it carried radar bombing systems that were essentially automated offset calculators. The AA-ANSQ-38 bombing navigation system could identify radar reference points, calculate wind drift, determine optimal offset angles, and fly the approach automatically. The bombardier's job shifted from manual calculation to system supervision, but the underlying principle was still Robert Williams's accidental discovery. Use crosswind drift as a weapon instead of fighting it. Vietnam proved offset bombing worked in an entirely different environment. The monsoon winds over North Vietnam were fierce and unpredictable, creating conditions worse than anything over Germany. B-52 formations bombing the Ho Chi Minh Trail would approach targets at offset angles calculated from real-time wind measurements taken by weather reconnaissance aircraft. They were dropping from 30,000 feet through winds that sometimes exceeded 150 miles per hour and still achieving accuracy that made trail interdiction effective. Post-strike reconnaissance showed that arc-light missions, the code name for B-52 raids, had average CEPs under 1,500 feet despite the challenging conditions. Then precision-guided munitions arrived and seemingly made offset bombing obsolete. Why calculate complex wind triangles when you could drop a laser-guided bomb that corrected its own flight path? The First Gulf War in 1991 showcased weapons that could fly through ventilation shafts, and military analysts declared the era of calculated bombing over. Computers and GPS would handle everything now, except they were wrong because they forgot about electronic warfare. Modern air defenses don't just shoot at aircraft, they jam GPS signals, spoof targeting systems, and create electronic environments where precision weapons become unguided again. When GPS is jammed, you're back to 1943's fundamental problem. How do you hit a target when your fancy technology stops working? The answer that the modern Air Force has rediscovered is offset bombing. Current doctrine for GPS-denied environments teaches bomber crews to use radar-identifiable features as offset reference points, calculate wind drift manually, and deliver weapons using geometry instead of satellites. The B-2 Spirit stealth bomber, the most sophisticated aircraft ever built, has offset bombing calculations built into its mission planning software, not as a backup but as a primary option for certain scenarios. When you're penetrating defended airspace where using active targeting systems would compromise stealth, passive offset techniques let you attack without radiating any signals. You identify reference points using synthetic aperture radar, calculate the offset angle that puts wind drift on your side, release weapons, and leave. The enemy never knows you were there until bombs start exploding. Even drone warfare uses offset principles. Reaper and Predator operators dealing with high winds at altitude will sometimes use offset aiming points for Hellfire missile attacks. The missile's guidance system handles the final approach, but the initial firing solution uses offset geometry to put the weapon in the ballpark. It's faster and more fuel-efficient than having the missile fight crosswinds for its entire flight. The technique has come full circle to where it started. Desperation breeding innovation. Modern military planners preparing for potential conflicts with peer adversaries assume GPS will be jammed or unavailable, so they're training crews on manual offset bombing with an intensity not seen since 1944. Flight schools are teaching wind triangles again. Bombing ranges are running offset approach practices. Someone in the Pentagon apparently read the after-action reports from D-Day and realized that the old ways still work when the new ways fail. Robert Williams and Charles Murphy probably never imagined their navigation error would influence warfare 80 years later. But that's how real innovation works. It solves the immediate problem so elegantly that it becomes permanent. Dropping bombs sideways and letting wind do the work wasn't just a World War II trick. It was a fundamental insight into physics, geometry, and how to turn environmental conditions into weapons. Every precision strike happening anywhere in the world today, whether GPS-guided or manually calculated, owes something to that confused October morning over Schweinfurt when someone aimed at the wrong target and accidentally hit the right one.